Hello, my name is Boyang Liu. I'm from OptNet Incorporated. Now I'm going to demo the optical Upper waveform generator on monolithic indium phosphide chip with continuously extendable duration based on our novel ultra-high resolution diffraction gratings. Here's the basic layout for our OAWG approach. It has two gratings. The left side demask grating, the right side mask grating. The input optical signal through the demask grating divided into different components. Each component has some specific wavelengths. All these components into different corresponding channels. On each channel, there are EA modulators and EO phase modulators. All the optical components then go through this masked grating. This grating will combine all the different components together into the output port. This diagram shows the channel response of the OAWG chip we are going to demo today. You can see it has 4 channels. Each channel has a very narrow band, about 100 GHz passband. The signal to noise ratio over 17 dB. Now let's move to the measurement setup for our OAWG-Demo. Okay, let's start with the chip on the measurement stage. Now what you are seeing is a real OAWG chip we fabricated. It's already mounted onto the measurement stage. This is on this small piece of wafer. There are tens of OAWG devices. Today we are going to demo one of them. This is a basic measurement setup for OAWG chip. This is a tunable laser provides optical input signal. This is a voltage pulse generator to provide modulation to the EA modulator on OAWG chip. The input signal coupled into the OAWG chip through this objective lens, and another objective lens at the end of OAWG chip, and all the optical signals collected by this objective lens and projected to this CCD camera, and also a high-speed photodetector. All the signal from the photodetector go into this oscilloscope, combined with all the other information, and go into this GPIB data collection unit. Now let's start the demo for OAWG chip. We firstly turn off the light, turn on all the CCD camera. We have 2 CCD cameras. This CCD camera to see the top view of the OAWG chip through this feed monitor. Through this monitor, you can see this device have 4 channels. Each channel have his own electrode. Electrode for channel 1, channel 2, channel 3, and channel 4. You can also see part of the grating, left side grating and right side grating. This is the electrode probe. This is the camera right after the output objective lens of the OAWG chip to see the output through this OAWG chip. Right now I'm going to turn on the voltage pulse generator to provide the modulation to the EA modulator on OAWG chip. I'm going to turn it on. So right now you can, through the CCD camera for the OAWG chip output monitor, you can barely see any output signal. The primary reason is each OAWG channel can only pass some specific wavelengths. Right now the wavelength is about 1521. Our previous measurement shows the central wavelength for the channel 1, this chip, is about 1524. So right now you cannot see any output through this CCD camera. Now I'm going to change the wavelength to 1524. Okay, right now you can see a very bright light spot over here. Now I'm going to replace this CCD camera with the photodetector. I'm turning on the photodetector. The output signal from photodetector go into this oscilloscope. So right now you can already see the modulated output signal from OAWG chip through this photodetector. And all the data from this oscilloscope go into this GPIB data collection unit. Now I'm going to do the wavelength scan to start the channel response for this OAWG chip. Generally, we scan a very long wavelength range, typically 50 nanometer. But right now, to save time, we just scan for a small range, 10 nanometer. Because this central wavelength for channel 1 is about 1524. We are going to scan the wavelength starting from 1520 to 1530.